Let's get started. Section 8.2, Dynamics of a single rigid body. In this section, I will review the classical mechanics developed by Newton and Euler. Okay, let's assume that rigid body is composed of a number of rigidly connected point mass. Okay, this is starting point. Okay, let me draw. Oh, this is the M1. This is the M2. Those are rigidly connected. It means the distance between both are same all the time. Okay. Maybe the total mass will be the sum of the each mass like this. And to make a notation of the position of M1 and M2, we should assign the frame. So let me assign frame here. Okay, here. This is the x-axis, y-axis, and the g-axis. Okay, let's assume that this is the body frame. Okay. Okay, let's assign a location vector. It is denoted by the R1 and the R2. This rigid body has the two mass, so the R1 and the R2 will have the opposite sign. Okay, here's M1 times R1 plus M2 times R2 can be zeros by adjusting the position of a body frame. Is it right? Because the R1 has the opposite sign of R2. Okay. Okay, this equality is satisfied at the time. This location will be the unique. This unique point is called as center of mass. Okay. Okay, if we have the three masses, maybe you can make another M3, R3. Those three sums will be the zero. At that time, we have the unique point. That point can be chosen as a center of mass. Is it right? Like this, you can extend a number of the masses in the body frame. Okay. Okay, let's assume that the body frame should be chosen at the center of mass all the time. Okay, here. One more. Assume that the body is moving with the body twist. Okay, here. Body twist applied here. Okay, maybe the linear velocity will be the VB. Maybe the angular velocity is the omega b. Okay, by combining both, we will call it twist. Okay, the body twist is applied to this rigid body, and then the pi here. Pi actually pi is the same with the Ri. But in the previous section, we have talked about Ri is the constant, fixed point. So we will replace it with the time-varying position of the Mi. So initially, Ri is the same with the Pi, but the rigid body is moving. At that time, the Pi can be changed according to the movement of the rigid body. Okay. Anyway, the Pi initially Pi is the same with the Ri. Okay. Okay, let's obtain the linear velocity of the M1. Okay. Okay, the linear velocity can be applied to both sides. Is it right? So VB and the VB appears at the both sides, and then the rotational velocity, the omega, will make the tangential velocity. Maybe if we choose like this, then maybe this one. This can be calculated using the cross product operator. Omega b cross Ri, maybe the P1. How about that? Maybe the omega b cross R2 or P2. Okay. Like this, we can write down the linear velocity of each mass, like this. VB plus omega b cross pi. Okay? This linear velocity can be written using the cross product operator, cross product skew symmetric matrix VB plus omega b matrix and pi. It can be it can be exchanged with the Ri here. Okay, it's very clear to obtain the linear velocity. Then let's take the time derivative to obtain the acceleration, linear acceleration. Okay, it has two terms, so the body acceleration will appear, okay, from here to here, and it has two terms, so omega b dot will appear first, and then pi dot will appear later. Okay, you're right. We know that the pi is equal to this one, so it can be applied to here. So it must be the pi dot. Okay. So we have the four terms: vb dot, omega b dot cross pi, omega cross vb, omega cross pi. Okay. If we apply the skew symmetric matrix form to instead of skew symmetric the cross product, this part is written like this. This is still like this. I'm sorry, this one. Maybe this is this one. The third terms appears like this. Last term will be this one, because last term is the omega cross pi. Okay, so it will be replaced with the matrix form pi and one more. So square matrix appear here. Okay, like this we can obtain the linear acceleration, okay, using the photon. Okay, in here the pi is replaced with the Ri all the time. It can be used exchangeable. Okay. Okay, taking a value that the Fy, maybe you know that this is Newton's law, Newton's second law. So once we obtain the linear acceleration, then we can write down this equation. Okay, so let's obtain it. The pi2 dot will be applied to here using the photon, and the moment, okay, let's assume that this is the Fy, this is the body frame, maybe this is the Ri. The cross product will make the moment, okay, Ri cross Fy. It can be written using the skew symmetric matrix form, okay, to replace the cross product operator. Okay, like this, we can write down the force and moment acting on each mass. Okay, by collecting every force and moment, we can make the length. Okay, here by collecting every moment, every linear force, then it can be replaced with the moment, total force, total linear force. By collecting the moment and the force, it can be defined using the length. Is right? Okay. Okay, so I will write down the generalized dynamics, including the Newton's law and Euler law later. Okay, before talking about that, the summation of mi ri must be the 0, because we choose the body frame at the center of mass. So it should be satisfied all the time. Okay, it can be extended to the cross product skew symmetry matrix form. Okay, so in this case, the 3 by 3 zero matrix appear. Okay, so we should mark in mind it is a zero vector, it is the zero matrix. On the other hand, if we have the three-dimensional vector A and B, if you take the skew symmetric form A using the three vector, the transpose will be the minus A. Is it right? This is a property of the skew symmetric. And A cross B, it can be written using the matrix form A and B. Is it right? So maybe you know that the minus A cross B will be equal to minus B cross A. Okay? So minus B and A. So if we exchange A and B vector, then minus sign is required. And A can be replaced with the minus N transpose. It is equal to the skew symmetric form of A. And then minus B and B transpose. Okay, the minus appear two times, so minus A transpose, B transpose. It can be combined. B skew symmetric and the skew symmetric and the transposer. Okay, this kind of property will be used to derive the generalized dynamics. Okay, first let's concentrate on the linear dynamics. Okay, maybe you know that this is a linear velocity. Is it right? Pi 2 dot. So by collecting every inertial pulse mi pi, we can obtain the linear pulse. Okay. Okay. Here, among four terms, VB dot and omega cross VB are independent of the Ri. So these two terms can be collected like this, and the third term will appear like this, and the fourth term. Okay. Okay, as mentioned before, I have talked about it, but it can be exchangeable using the minus sign. Is it right? So if you write down summation I mi ri minus and omega b, maybe you know that according to the definition of the center of mass, it is 0. From here, we can perceive this property is satisfied. Okay, so it is 0. One more. On the other hand, the mi can be inserted to here because it is a scalar. So summation of the mi ri, it must be 0 if you choose the body frame as a center of mass. Okay, so we have just two terms. Okay, here, actually this is the inertial force, this is the linear momentum. Okay, linear momentum should be multiplied to the angular velocity cross product. Okay. Okay, let's focus on the rotational dynamics. R cross F is the moment. So Fi, in the previous section, Fi will be applied to here. Okay. As mentioned before, Fi has the four terms. 1, 2, 3, 4. Okay. Okay, the first and the third term independent of the Ri. So let's collect these two vectors to here. Okay. And third term and the fourth term appears like this. Third term and the fourth terms. Okay. In front side, both two terms are independent of the Ri, so we know that this vector appear in front of these two terms. Okay, according to the definition of the center mass, it must be the zero matrix. Okay, so it will disappear. Okay, and then from here, if we exchange these two terms, then the minus will be required, and then the Ri matrix appears two times, and then omega b dot. Okay, one more. It has the two square matrix, so one is exchangeable, Ri and omega b. So minus will appear. So mi, Ri, omega b. I'm sorry, this omega b and Ri and omega b. Okay, it should have minus sign. Both are exchanged. Okay, one more transpose can be chosen, and then these two matrices can be exchangeable, Ri and the transpose. So these two parts can be combined each other. So minus omega b cross Ri square omega b. Okay, it can be written here. Okay, the m is a scalar, so let's this part can be replaced, can be inserted here because it is scalar. So let's collect minus summation mi Ri square. Okay, from here, like this. Okay, let's assign these terms as a body rotational inertial matrix expressed in the center of mass. Okay, if you choose the other frame, it cannot be satisfied. But if we choose the body frame at the center of mass, we can write down the moment of inertia using this equation. Okay. So let's denote this part as IB, okay? Body frame inertia, body inertia, and this is also IB. So we can write down IB omega b dot plus omega b, IB omega b. Okay, let's compare this rotational dynamics with the linear dynamics. Okay, FB is equal to mb vb dot plus omega b cross mb vb, linear momentum. On the other hand, the rotational dynamics, the moment can be written ib omega b dot plus omega b cross linear angular momentum ib omega b. As you can see here, the dynamics can be written very similar forms. You right? Okay. As you know, that this is the linear momentum, this is the angular momentum. Okay. Okay. As you know, that this is the Newton equation, this is the Euler equation. So Euler equation for the rotating rigid body. Okay, if you wanted to calculate kinetic energy of the rotating body, maybe you can use this equation. But this IB is the constant matrix, not varying matrix. This is constant. That is different between the mass matrix and the inertial matrix. Okay. Okay, let's obtain the individual element of the IB, moment of inertial matrix. Okay. Okay, as you know, that this is the definition. Okay, minus summation mi Ri square. Okay, you know that Ri skew symmetry form of the Ri is written like this. This appears 2 times. Okay, let's multiply the first column, first row and the first column. Then we have the minus gi square minus yi square. But minus appear again. So this is the positive part. How about the 1 by 2? Okay, 1 by 2. We have the xi, yi. We have the minus sign. So minus summation mi, xi, yi. Okay, like this we can complete the 9 element of the inertial matrix IB. Okay, let's make a notation about the first element. 1 by 1, this part will be denoted by the ixx. The 1 by 2 is dependent on the xi and yi, so ixy. Okay, this is the ixz. This is the ixy. Okay, actually the both terms are same each other, so inertial matrix is symmetric all the time. How about that? There is no y, so it depends on it can be calculated using the y-axis. So it is called as y, I, y, y. Okay, I, y, z, I, x, z, I, y, z. It is obtained in the axis of the g, so I, z, z. Okay, like this we can obtain the 9 element, actually the 6 element, because it has a the symmetry matrix form. Okay, this is the point mass. This is about the point mass. Okay, it can be extended into the volumic integral. Okay, here 1 by let's assume that the 1 by 1 element. Let's consider 1 by 1 element. This is the I, mi, and yi square, zi square. Okay, it is about the particle, the point mass. But let's assume that rho is the density. Density is defined as a mass over volume. Okay. In the case of steel or aluminum, this will be the constant. Is it right? So the density is the constant. Okay, the mass will be equal to rho v. Okay. Let's take the variation of the m. The dm, rho is the constant, rho dv. Okay, maybe you know that the definition of the integral, the summation can be changed into the integral. Okay, my can be changed as a dm. So rho dv will appear later part, and the integral should be obtained in the volume because you are using the volumic integral here. So the rigid body volume can be denoted by the b here. Okay, so b, this is the volume. And then y square and z square, like this. So the point mass moment of inertia can be exchangeable into the volumic integral, okay, like this. So it is equal to this one. So Ixx can be obtained using the integral over the volume y square plus g square rho dv. Rho must be the constant. Okay. If you are using the pneumatic or hydraulic source, we should consider the bearing law, the bearing density. It makes the problem difficult. At that time, the inertia is varying. Okay, but in the case of the rigid body, if you choose the body frame at the center of mass, this I-axis, this I-XY will be the constant. Okay. So like this, we can obtain the moment of inertia, I-XX, I-YY, ZZ, and XY, and XZ, and YZ. It is a formal definition of moment of inertia. Okay, let's take an example. From here, the first example is about the rectangular. Okay, let's obtain the I-XX. I'm sorry. Okay, I-XX. Maybe you know the definition will be like this. Volume and y square, g square, rho dv. Okay. So it is obtained in the plane of the YG axis. Is it right? So let's project this rectangular into the x direction. Then we have, this is the y, this is the z. Okay, maybe we will have the rectangle. It can be obtained in viewpoint of the x-axis. Okay, so this is the w, so it is the w over 2, maybe the negative sign. How about that? This is the height, 1 over h over 2. Okay, let's take the small mass. The coordinate value of the y-axis will be the y. This is the z. Okay. Maybe this mass will be denoted by the rho dv. Okay. Okay. Let's obtain this integral. Okay, this integral can be separated using the three elements, such as, in the case of the axis, minus L over 2 plus L over 2 in the viewpoint of the x, and minus W over 2, and the z will be h. So h over 2 minus h over 2. And then y square and the g square, and then the constant rho, and dz, dy, dx. Okay? Okay, the inner part can be integrated. Okay. Y square is the constant viewpoint of the z, so z, and z cube over 3. And then we will apply the initial h minus h over 2, okay, and then rho. This one, okay, let's obtain it. Rho, and then y square, h over 2 minus h over 2, so h. And this will be applied to here. Maybe it h cube over 24. Is it right? Okay, that's right. So, and then minus h cube minus 24. Okay, so it can be written rho h square y square h and h cube over 12. Okay, the first integral provides this equation. Okay, and then let me change the color from here to here in viewpoint of the y. Okay, this can be this should be integrated from the w over 2 minus w over 2 to the w over 2. Okay, let's take the integration in point of y. Okay, here log and then y square, maybe the y cube over 3, and h is constant here, h cube over 12, and then y. Okay, the initial and the final value w over 2 minus w over 2. Okay, okay, here log, and then it will provide h w cube over 12, and then h here. One more h cube over 2, and then w. Okay, like this we can write down log w h and the w square and the h square. The last element is about the integration of the x, but x is the constant here, okay, because we are projecting the input point of the axis, so L should be applied to here. So last one will be the log WHL, okay, and then 12 W square H square. Okay, let's assume that, let's consider this is this volume. This volume will be WHL. So this is the volume. Okay, is it right? Log V is equal to mass. So mass over 12 W square H square. Okay, it is equal to Ixx. As you can see here, we can obtain the x-axis momentum inertia. Okay, the procedure is a little bit difficult, but we can know that we should know how to obtain it. Okay, let's move to maybe the cylindrical and the ellipsoid will provide a different form of Ixx and IOII. But if the symmetric, I think the figure 8.5 provides the symmetric form of the each axis. At that time, the Ixy will be the 0. Okay? If you take the unsymmetric form of a shape, then this part will appear. Okay? Okay, if the body has the uniform density, the IB is determined by the shape of this body, because the rho is the constant, so it depends on the y square or z square. So it is only dependent on the shape of the lead body. Okay? Okay, the IB matrix will be the 3 by 3. Moreover, it has the symmetric form. So if you take the eigenvalue decomposition to here, anytime, all the time, we can make this matrix into the diagonal form. Is it right? If you know the eigenvector, then any matrix can be diagonalized. Okay, so if you know the eigenvector, the major axis can be chosen along with the eigenvector. Maybe you can know the minor axis. Like this, the principal axis of the inertia is aligned with the axis of the body frame. Both frames are each other. Then off-diagonal term will be the 0. Okay? It can be chosen. It can be satisfied all the time if we know how to derive the eigenvector of any matrix. Okay. So IB can be written using the major axis only. The other part will be the 0 if you know the eigenvector. Okay, 0, 0 and IZZ. Okay, if you apply this diagonal matrix to here and here using the omega b, then we can obtain the simplified Euler equation. Okay, here inertial matrix IB can be expressed into any rotated frame. Okay, this is the any rigid body. Maybe this is the center mass. If we take the body frame B along with the eigenvector, then we have this kind of diagonalized inertial matrix. Okay. Here, if you choose rotated body frame, okay, it is denoted by the C. Okay. Maybe this rotation will be the R, BC or CB. It can be expressed, can be possible. Okay. Anyway, this is the C. Okay. If you know the rotation matrix from the body frame B into the new frame C, okay. Here, we know that the kinetic energy is independent of the chosen frame. Is it right? Energy is just the energy. It is not dependent on the frame, the coordinate. Okay. So the rotational energy in terms of the C frame, in terms of the B frame, both are same as a scalar value. Okay, here the omega b can be written by using the rotation matrix RBC, okay, omega c. Is it right? We know that the subscription cancellation rule, it will be equal to the omega b. So omega b, these two matrix vector equation will be applied to here and here. Then we have this equation. Okay. By taking a transpose operation, then we have this one. It should be equal to IC. Is it right? So the inertial matrix, 3 by 3 inertial matrix can be expressed using the rotated frame. Okay. Okay, this concept can be multiplied to the this concept can be applied to the some parallel axis theorem. Okay, this is the any rigid body. Okay, here the center mass over here. If you take some coordinate like this, let's move to the other point. The coordinate is aligned with the B. Anyway, this point is the Q. Okay. In the previous slide, we have talked about just the rotation matrix. In here, theorem 8.1 is about the moving in the parallel side or along with the same axis, but the distance can be chosen as a Q vector. Okay. So the inertial matrix IQ about the frame aligned with the B, there is no rotation between B and Q, but at a point Q, okay, two frames, there is no rotation, but some displacement appear as a Q related to the inertial matrix IB calculated at the center mass. Okay, this is the center mass moment of inertia, and then we will apply Q transpose Q as a scalar value times identity matrix minus Q Q transform, outer expansion of the Q vector. So we either make the 3 by 3 matrix and then mass matrix is multiplied as a scalar value. Like this, we can move the inertia matrix into the other plane. Okay, align with the center mass plane. Okay, it is called as a Stainer's theorem. Later, the Stainer's theorem and the rotated frame inertia can be combined into one equation. But now we are suggesting the two independent rule. The first one is about Stainer's theorem. The other one is about the rotational moment of inertia. Okay, the Stainer's theorem can be simplified in the case of the planar case. Okay, let's assume that we have the planar space. This is x-axis, y-axis. There is some pendulum. Okay, maybe you can calculate the ICM. Okay, center mass moment of inertia as a scalar value because we are talking about the plane, not special case. So the ICM, maybe in this case, it will be equal to the zeros because the point mass, I'm not sure the point mass has some moment of inertia anyway. And then the distance is the d. At that time, in the case of this axis, it will be equal to md squared. Actually, it is the easiest version of Stainer's theorem. Okay, Stainer's theorem is about a three-dimensional case, but if you reduce your attention to the one-dimensional case, then we have the parallel axis theorem. Okay, parallel axis theorem will be applied to the 0x omega, 0y omega, but omega g should appear, maybe the omega g. Okay, till now I have talked about the classical mechanics using the momentum of inertia concept. I think you should be good at how to obtain the moment of inertia. That is the play a core role in driving the equation of motion. Okay, the linear dynamics and the angular dynamics will be combined into the twist Lenz's formulation. Actually, this formulation is very beautiful, so I'd like to recommend you to use this formulation later. Okay, the linear dynamics. Maybe we have derived the linear dynamics like this. Do you remember that? On the other hand, the rotational dynamics. Okay, both follow the same form each other. Okay, let's combine the linear dynamics and rotational dynamics. Okay, maybe in order to make the Lenz, the moment will appear first. Okay, IB and omega B dot and omega B cross IB omega B. It complete rotational dynamics. On the other hand, the linear dynamics is the M VB dot omega B cross M VB. It makes the linear dynamics. Okay. Anyway, we can combine these two independent dynamics using the 3 by 3 zero matrix. Okay, it's very easy. Okay, 3 by 3 matrix appear off diagonal side. Okay. Here we know that the V cross V must be the zero, is it right? So it can be written using the skew symmetric form. V and V is the zero. So we will use this property. Okay. From this part, let me add skew symmetric form of the VB. Okay, like this. It does not affect, does not influence in total dynamics. Is it right? Okay, this part will be applied to here. It will be the zero. This part will apply to later. Okay. Okay, let me write down again this one and this one. It's the same. This one is the same. Okay, this one will be a VB skew symmetric mass, and later VB will be applied. So it is a zero. So if we add skew symmetric form of the VB into the 1/2 block matrix, it does not have any effect on the total dynamics. Okay, it is the ideal of a twist Lenschi formulation. Okay, so we will add this term, and maybe you know that the omega b skew symmetric form, maybe this is equal to minus omega b transpose. Transpose of the skew symmetric will produce the minus sign. So this is the same. So we will apply it to here and here and here. Okay. So minus omega b and minus VB transpose and 0, 3/3 zero matrix, minus omega b transpose. Actually, this matrix is same this one. Okay, let's extract the minus sign in front side, minus omega b transpose, VB transpose, 0, 3/3, omega b transpose. Okay, transpose operator can be extracted outside, then minus omega b, 0, and VB, and omega b. And then we will take the transpose here. Okay, so the minus sign and this matrix can be exchangeable like this using the transpose operator. Okay, as mentioned before, this part does not affect any dynamics. Anyway, we will use this equation to derive the twist matrix Lenschi formulation. Okay. Okay. In order to derive the six-dimensional special dynamics, we will use the twist and the Lenschi. We know that this is the twist, this is the Lenschi. Every expressions are obtained in terms of the body frame, okay, not space frame. Okay, in the front side, let me assume that it is special. It is special inertia, okay, belonging to R 6 times 6. So we will introduce this concept, special inertia matrix, like this, okay? And the total energy in terms of the rotational and the translational will be combined using the twist and the special inertia, okay? Because this is a 6x6 matrix. It is related to rotation, it is related to the translation. So we can combine the kinetic energy. Okay, one more. Let's assume that the special momentum denoted by the PB, GB, VB. Okay, in the previous slide, the body length can be written GB, the time derivative of twist, plus some matrix, maybe this is a minus, the transpose will be applied, and then GB, VB, the special momentum. Okay, it is very similar with the linear dynamics. MB, VB dot, omega B cross MB, VB. On the other hand, the angular rotational dynamics is the IB, omega B dot plus omega B, IB, omega B. Do you remember these two equations? This equation can be combined into one equation using the six-dimensional vector. Okay, just we have the one issue here. Okay, maybe these terms can be written minus omega B and omega VB, and how about that, VB, okay, and zero matrix. I'm sorry, this is the omega B transpose. Okay, we don't know this notation. According to the previous linear dynamics and the rotational dynamics, it is corresponding to the cross product operation. Okay. Anyway, let's move to the next issue. Okay. This matrix can be thought of generalization of cross product operation. Okay, so this you should remember that this matrix as a generalization of a cross product operation. Okay. Okay. Here, the cross product of two vectors, the three-dimensional vector W1 and the W2 are given. At the time, the cross product of the W1 and the W2 will produce a three-dimensional vector. If we take the skew symmetry matrix form, then we have this identity. Okay. In the case of the matrix form of operation of a cross product, can be decomposed W1, W2 minus W2, W1. Okay. We will use this notation later. One more. For given two twists, V1 and V2 as a six-dimensional vector, here we will perform the calculation analogous to this one. So V1 skew symmetric form, V2 matrix form of the V2 as a 4x4, V2 and V1. Okay, maybe you know that the matrix form of V1 will appear W1 matrix form of W1 and V1 as a vector, W2 and V2, W2, V2, W1, V1. Okay. Okay, let's obtain this calculation. Then the first 3x3 element will be the W1, W2 minus W2, W1. Okay, second term will be W1, V2 minus W2, V1. Okay, it can be combined as a new W prime. Okay, and then it is the vector, so V prime. Okay, W prime will be equal to W1 cross W2. Okay, if we take the matrix form, maybe those are same. It is obtained W1, W2 minus W2, W1. Okay, One more, the v prime is the vector as a three-dimensional one. It is w1 v2 minus w2 v1. Okay, here these two vectors can be combined into the six-dimensional vector. Okay, w prime will be equal to w1 matrix form cross product and w2. So w1 matrix form and w2, and v prime is equal to v1 matrix form and w2. Okay, let me write down the v1 w2 plus w1 v2. If we exchange these two notation, then we need to minus sign. So w1 v2 minus w2 v1. Okay, so we have this equation. Okay, so this 6 by 6 matrix will produce another twist from the given twist. Okay, the twist can be exchanged into the other one. Okay, so actually this 6 by 6 matrix perform the cross product operation between the V1 two twists, V1 and V2. Okay, so it is the generalized form of cross product operation between V1 and V2, two twists. Okay, actually this cross product, the generalization of cross product of the two twists V1 and V2 is called as Lie bracket. Okay, Lie bracket of V1 and V2. Okay, let me denote the Lie bracket small adjoint V1, because the element is the V1 and W1. Okay, take the matrix, it will be the 6 by 6, and then V2, because this is the second twist, it will produce new twist. Okay, the definition 8.1, given two twists V1 and V2, the Lie bracket of V1 and V2 will be written using the small adjoint V1 and V2, or adjoint V1, V2. Okay, adjoint V1 or the Lie bracket of the V1 like this. The V2 will applied to here, then it will produce new twist. Okay, it plays on cross product operation. Okay, so we should remember the element is the V and W, then adjoint matrix, small adjoint matrix will appear in the dynamics. Okay, so let's come back to our focus to the original matrix. Okay, in the case of the single rigid body, how about that? This is equal to Lie bracket of VB transpose as a minus sign. Okay, as you know, this is the GB, this is the twist, this is the GB, special inertia, and time derivative of twist. So if you write down this equation as a one equation, body twist GB VB dot minus Lie bracket of VB and the linear momentum, the special momentum. Okay, so it can be written using the bracket notation as a joint VB transpose. Okay, both are same each other. Okay, let's write down the combined equation. The body length is equal to special inertia time derivative of body twist minus other joint VB transpose GB VB. Okay, it is conclusion of this section. On the other hand, the linear dynamics FB MB VB dot plus omega B MB VB. Okay, if we take the transpose operation, maybe this term will be the minus sign. Okay, the moment rotational dynamics MB is equal to IB omega B dot minus, at the time the transpose operator is required, omega B transpose IB omega B. It looks like generalization of a cross product operator, right? It is corresponding to the omega B. So the rib bracket or the joint VB will be used to derive the equation of motion. Okay, on the other hand, the rib bracket of the VB can be applied to the FB, F here. Okay, maybe you know that the rib bracket of the twist V can be multiplied to the body twist, then it will be equal to this equation. Sometimes it can be used, so we just show the result of the rib bracket of the V and the F. Okay, the energy is independent of coordinate frame. So in the case of A frame, we can write down the total energy using the GA and the VA using the body twist. Okay, it can be written into the other frame using the B. Okay, maybe you know that the body twist, any twist, can be transformed using the other joint. We have learned it in chapter 3. Here, TBA and VA can be applied. Okay, if you have the TBA as a rotation matrix and the position vector and the 0, 0, 0 and 1, that RP is used to compose of the other joint. Other joint TBA will be equal to R 3 by 3 zero matrix up here and P cross R. Okay, if you know the homogeneous transform, then we can write down the other joint matrix to transform the body twist. Okay, so the VB twist can be written using the other joint operator or more. Transpose is applied. At that time, the sequence is conversed. So VA and the VA. So inner three terms will be equal to GA. Actually, it is the generalized version of what? Steiner's theorem. Okay, including rotation and translation. Okay, so the special inertia matrix GA in the frame A, it can be obtained using the other joint matrix like this. As mentioned before, this is a generalized version of Steiner's theorem, including rotation and the translation. Okay, one more. If you take the other frame instead of the body frame, such as the A here, it can be chosen anywhere. At that time, if you exchange the B into the A, like this, will be effective, will be used for the derivation of dynamics. So the equation of motion is independent of the frame of representation.